Welcome to AI Paperslop. Today we are tearing straight into AREX, which stands for Towards a Recursively Self-Improving Agent for Deep Research.
From the Beijing Academy of Artificial Intelligence, right? BAAI.
Exactly. And look, if you're building agentic systems right now, you need to understand this architecture immediately.
It's basically required reading at this point.
Yeah. So here's the ultra-dense summary. AREX solves the long horizon research problem by exploiting something called discovery verification asymmetry.
Which is such a brilliant framing.
Right. Instead of just telling an agent to search endlessly, it uses a two-loop architecture.
Yeah.
You've got an inner loop for evidence gathering and an outer loop for constraint-wise verification and self-improvement.
And it handles infinite context, which is the real kicker.
Yes. Crucially, it manages infinite context natively. It uses this autonomous context update tool that basically compresses its own history into a verified state without relying on external summarization models.
Which saves so much overhead.
Completely. And BAAI trained this using long horizon reinforcement learning with hierarchical normalization.
The math on that is actually insane. We'll get into it.
Oh, we are definitely getting into it. But the result is that a 4 billion parameter dense model and a 122 billion parameter MoE model with only 10 billion active parameters are rivaling vastly larger closed-weight models.
I mean, we're talking absolute gauntlets like GAIA, Humanity's Last Exam, and BrowseComp.
So that's the high-level view. But I want to transition to the fundamental problem here. Why do current agents fail at deep research? Because standard industry logic is just, give it more compute, right?
Yeah, just tell it to search longer or sample 100 more trajectories.
But that doesn't work.
No, it's completely backward. And this is a dense, incredibly high-signal paper because it tackles the exact wall that every ML engineer listening to this has hit.
The compounding error problem.
Exactly. The core issue with simply searching longer is error compounding. I mean,
Wow.
If your agent takes a wrong turn on, say, step 40 of a 100-step task, generating more tokens in that wrong direction doesn't help at all.
It just hallucinates further down the rabbit hole.
Right. It just solidifies the mistake. AREX steps back and addresses the fundamental nature of how we actually solve complex problems.
Which they define as discovery verification asymmetry. And I really want to conceptualize this because it's the bedrock of the whole paper.
It is the entire philosophy behind the architecture.
So think of discovery like a detective trying to build a case in a massive city. You're dropped into a metropolis with millions of people, right?
Sounds exhausting.
Yeah, and you have to find the exact combination of obscure clues that identify a single suspect. The search space is gigantic.
And the signal is incredibly sparse.
Exactly. The computational cost of finding that specific combination of facts in the wild is astronomically high.
But verification, so proving you have the right suspect, is an entirely different computational problem.
Right, because once you have a suspect, it changes.
Right. If that detective brings a candidate suspect to a judge, the judge is not searching the whole city. The judge is going down a localized deterministic checklist.
Does the suspect match the physical description?
Exactly. Is their alibi temporally valid for the time of the crime? Do their financial records align?
It's highly tractable.
Highly tractable. It can be decomposed into very specific constraint-wise checks. Finding an answer that jointly satisfies multiple overlapping constraints is incredibly difficult, but...
Evaluating a proposed candidate against those constraints is much, much simpler.
Exactly.
But hold on, let me play devil's advocate here. Don't we already have verifiers in our agentic pipelines?
Sure we do.
I mean, most state-of-the-art frameworks use some form of verification to grade outputs, don't they?
We do, but look at where they are actually positioned in the pipeline. They almost always use verification at the very end of the process.
Oh, right, like a reward model.
Yeah, you generate a dozen candidate trajectories, run them all the way to completion, and then use a verifier to rank the final answers and pick the best one.
Or maybe make tiny tweaks mid-flight.
Right. What makes AREX fundamentally different is that it uses verification to define the actual transition between research rounds.
So it's not just grading the final exam, it's like a diagnostic test right in the middle of the process.
Exactly. By evaluating a provisional answer, the agent isn't just asking, is this completely right or completely wrong?
What is it asking them?
It isolates exactly what it currently knows to be true, pinpoints the exact remaining uncertainty, and then formulates a highly targeted next step based on that delta.
Oh, wow.
Yeah, think about your own engineering workflows, right? For the listeners out there building multi-file code bases, If one unit test fails, you don't throw away the entire repository and start typing from scratch.
You'd never get anything done.
Right. You isolate the failure, preserve the working code, and patch the bug. AREX gives that exact iterative patch and improve workflow to a language model.
Okay, so to physically execute that kind of workflow, BAAI designed this dual loop architecture. Let's break down the mechanics of that.
Let's do it.
It starts with the inner research loop, and this is the engine doing the actual legwork, right?
Yeah, the heavy lifting.
You give the agent an objective, and it invokes its search tools, reads raw text from the web, runs intermediate analysis, and eventually builds what they call a provisional answer.
And honestly, that inner loop behaves largely like the exploratory agents we are all already building. It executes actions and appends those interactions to its trajectory.
So it's pretty standard up to that point.
Right. The real architectural shift happens when the inner loop pauses and passes its output to the outer self-improvement loop.
It doesn't just dump a wall of text, does it?
No, it outputs a structured finish. This contains the provisional answer, the supporting evidence with specific document identifiers, and crucially, a confidence score from 0 to 100.
Wait, I have to push back here. We know language models are notoriously overconfident.
Oh, incredibly overconfident.
Right, and prone to hallucination. So if the model is essentially grading its own homework to decide if it should move on, how does it not just confidently hallucinate a 99% score and derail the entire research loop?
That is the exact trap. And it's why the confidence score isn't just a generic vibe check. It is a rigorous, constraint-wise audit.
So it's forced to show its work.
Exactly. The outer loop forces the model to evaluate the completeness of the answer against the original prompt, the logical consistency of the facts, the provenance of the evidence.
Meaning, did it actually cite a real retrieved document, or did it just invent a source?
Right. And temporal validity. Does the timeline of events actually make sense based on the retrieved dates? It has to justify the score based on those extracted constraints.
Okay, so what happens if it passes?
If that rigorous score is high exceeding a predefined threshold, the outer loop accepts the final answer and the task terminates successfully.
But in deep research, that first attempt is almost always going to be incomplete.
Almost inherently, yeah.
Right. Let's say the task is to find the total revenue of 3 specific subsidiary companies in Q3 of 2023.
Classic complex query.
The inner loop finds 2 of them, but misses the 3rd. So the confidence score comes back low. Does it just scrap the whole trajectory, start over, and waste all that massive compute it just burned reading financial reports?
This is where the trajectory assessment mechanism saves the system. The outer loop looks at the failure and categorizes the trajectory.
Categorizes it how?
Well, if it is hopelessly noisy, say the agent latched onto a completely hallucinated premise early on and read 10 irrelevant websites, it triggers a restart action.
It clears the board entirely.
Yes, completely flushed. But if the trajectory is recoverable, like in your financial report example, it triggers a refine action.
Ah, so it salvages the verified data.
Exactly. It takes that partially verified state the 2 companies had successfully found revenue for and generates a highly targeted objective for the next inner loop.
So it rewrites its own prompt.
Yes. Instead of the prompt being find the revenue for these 3 companies, the new objective becomes you have confirmed company A and B. Now specifically search for the Q3 2023 revenue of company C.
And the inner loop fires up again, but with laser focus.
Exactly.
Which sounds incredibly efficient until you think about the hardware realities.
The token explosion.
Yes. If you have an agent recursively looping like this, running inner loops, scraping raw HTML from corporate sites, generating discarded plans, refining and looping again, the context window is going to explode.
It's inevitable.
You are going to hit 128K or 256K tokens so fast. And if you've ever watched an agent's attention mechanism degrade into absolute mush at high token counts, you know exactly how painful this is.
It just forgets everything from the beginning of the prompt.
Right. So how does AREX sustain this over long horizons without drowning in its own token exhaust?
It is the ultimate technical bottleneck for recursive agents. Historically, the solution to token explosion has been to bolt on a separate external summarization model.
Like a smaller llama model or something on the side.
Right. You pause the main agent, feed the massive context to a smaller, cheaper model, ask it to summarize the state, and paste that summary back into the main prompt.
Which is so clunky.
It's clunky, it loses critical nuance, and it fundamentally breaks the agent's reasoning flow. AREX solves this elegantly by learning an autonomous context update tool natively.
Meaning the policy itself decides when and how to compress its memory.
Yes.
It's just a tool it can call, like searching the web or using a calculator.
Exactly. The inner loop can optionally trigger this context update tool whenever it feels its context is getting bloated.
That's wild.
When it does, it compresses the massive interaction history into a compact improvement state.
I like to think of it like a detective's whiteboard.
That's a good analogy.
At first, the board is covered in random photos, string, dead-end leads, scribbled notes. And what this tool does is actively wipe the board clean of all the junk.
It just purges it.
Right. It throws away the raw HTML tool responses, the discarded planning steps, the failed searches. And what gets pinned back up on the clean whiteboard is exclusively the verified evidence and the unresolved constraints.
And this is the profound aha moment of the paper. By giving the agent a working memory that it curates itself, BAAI has taken a hardware scaling law problem, the fixed context window, and turned it into a reinforcement learning optimization problem.
Wait, so memory curation literally becomes an action space.
Exactly. The agent learns through RL that if it fills its context window with uncompressed junk, it will eventually fail the task and receive no reward.
Wow.
So it actively learns to manage its own cognitive load.
That is a massive paradigm shift, but it brings up a huge mathematical problem.
The credit assignment problem.
Yes. If this agent is autonomously managing its memory, refining its state, and running these massive loops, how do you actually train the RL policy?
It's notoriously hard.
In long-horizon reinforcement learning, the rewards are so sparse. If the agent takes 150 steps and finally gets the answer right at the very end, how does standard RL not just completely lose the signal?
It usually does.
Right. How does the policy know that step 42, where it updated its context, was the critical move, and not step 89, which was just random noise?
Standard algorithms will just smear the reward across all 150 steps, which teaches the model almost nothing. BAAI attacked this on two fronts, highly specific reward shaping and a custom training objective.
Okay, let's start with the data.
Right. First, they didn't just use toy examples. They used human experts to define complex templates for browse-intensive synthesis and deep scientific literature integration.
And they populated these templates with real-world sources and explicitly extracted constraints, right?
Yep.
Temporal constraints like must be published after Q3 2023, numerical properties, and entity relations. This forces the model to synthesize multiple sources because a simple keyword match just won't satisfy all those constraints simultaneously.
Exactly. And during the RL phase, they shape the reward to emphasize specific high-value intermediate steps. The model does not just get a binary reward at the end.
So it's getting breadcrumbs along the way.
Right. The loss function heavily rewards evidence discovery when it finds a verifiable piece of the puzzle. Crucially, it rewards path rejection.
Oh, that's interesting.
The model gets a positive signal for realizing it is at a dead end and turning back, rather than hallucinating forward. And it receives targeted rewards for executing those key context updates to keep its memory clean.
But even with intermediate rewards, you still have a gradient problem, don't you?
You do.
Because trajectory lengths vary wildly. Let's say Trajectory A solves a problem in 5 steps, so it produces 5 data points for the loss calculation.
Sure.
But Trajectory B gets lost and takes 100 steps to fail, producing 100 data points. If you do standard policy gradients over a batch, won't the incredibly long, meandering trajectories just mathematically hijack the gradient updates because they have 20 times the weight?
Yes, absolutely. If you use a standard proximal policy optimization PPO objective, those long, messy trajectories dominate the training simply because of their length.
The model might actually learn that taking more steps is a valid policy behavior.
Exactly. To prevent this, BAAI implemented hierarchical normalization in their RL objective.
Okay, walk us through the math on that. How does it neutralize the bias?
Instead of a flat average over all the thousands of steps in a training batch, they normalize hierarchically.
Meaning in 2 stages.
Right. First, they average the loss over the assistant steps within a single trajectory. So whether trajectory A took 5 steps or trajectory B took 100 steps, each trajectory is compressed down to a single normalized loss value representing that specific run.
I see.
Then they take the average of those trajectory level losses across the entire rollout group to compute the final gradient update.
That is brilliant. It completely flattens the weight.
It really does.
Every attempt at a problem gets an equal vote in the gradient update, regardless of how many tokens it burned. It forces the model to actually learn step efficiency, rather than just learning to survive long rollouts.
And they pair that with a KL penalty. For those tuning RLHF systems out there, You know that optimizing heavily for specific rewards can cause the model's fundamental language capabilities to degrade.
Right, it drifts into mode collapse.
Exactly. The KL penalty compares the agent's current policy against a reference policy, penalizing it if it diverges too far from natural, coherent reasoning. It's really a masterclass in adapting standard RL techniques for the specific pathologies of long-horizon tasks.
Okay, so all of this architecture and training math is fascinating, but for the engineers listening, it all comes down to the benchmarks.
Always.
Does discovery, verification, asymmetry actually work in the wild? Let's look at the models they instantiated. They built two versions. AREX Turbo, which is a tiny, dense 4 billion parameter model,
Really small.
and AREX Base, which is a 122 billion parameter mixture of experts model. But during inference, AREX Base only activates 10 billion parameters.
So these are not 400 billion parameter monolithic behemoths. They are highly efficient, targeted models.
And when you look at the benchmark results, the effect of this recursive self-improvement architecture becomes undeniable. Let's convert these numbers into reality. Take GAIA, which is basically the gold standard for complex multi-step agentic reasoning right now.
It's brutal.
It is. AREX Base scores an 85.4. That beats Gemini 3.1, which scored an 80.6. It beats Qwen 35B, which got exactly 80.0.
Beating a model like Gemini 3.1 on GAIA with a model that only activates 10 billion parameters is a massive validation.
It's crazy.
On GAIA, standard models will often pull a document, misread a table, and confidently output the wrong answer. Because AREX uses the refine action, if it pulls a document and the outer loop detects a missing constraint, it backtracks.
It catches itself.
Right. It actively patches its own mistakes before finalizing the output.
And we see this even more clearly on BrowseComp, which tests deep web navigation. Imagine an agent having to navigate a bloated, constantly shifting government database to synthesize 3 different demographic reports.
Standard models just get lost in the HTML.
Completely lost. But AREX Base hits an 82.5, right behind Kimi K2.6 at 83.2, and well ahead of GLM5. But honestly, the real story is the tiny model.
The turbo model.
Yes. AREX Turbo, the 4 billion parameter dense model, hits 70.7 on BrowseComp. It absolutely crushes the much larger Qwen 35B, which only scored 61.0.
Think about what that means for inference costs.
It's massive.
A 4 billion parameter model is outperforming a 35 billion parameter model by nearly 10 absolute percentage points on a complex browsing task. You are trading raw, brute force parameterized knowledge for active algorithmic reasoning.
You don't need a dense 100 billion parameter model to do deep research.
Not if you structure a smaller model to actively verify its own hypotheses and autonomously manage its own context.
It fundamentally rewrites the scaling laws for agentic workflows. And just to round out the stats, on XBench 2510, AREX Base secures a 71.0, while the Turbo model gets a 57.0. The takeaway for every ML practitioner listening to this deep dive is clear, intelligent looping and memory curation can punch leagues above their weight class.
For sure. And as we wrap up this deep dive, I actually want to leave you with a broader implication to consider.
Let's hear it.
We have spent the last few years obsessed with expanding the context window. 32K, 128K, 1 million, 2 million tokens.
It's just an arms race of hardware and attention mechanisms.
Exactly. But if an agent like AREX can recursively verify its own outputs and autonomously curate its own context window, perfectly compressing its history into verified states and unresolved constraints without an external model, are we approaching the end of the fixed context window era?
That is a wild proposition. You're saying the window size might just stop mattering.
Think about it. If a model can perform this compression indefinitely without losing task-critical signal, future AI models might become perpetual, continuous running entities.
Because they never fill up.
Right. They would never truly need to be restarted or have their context flushed because they ran out of room. They would stop acting like transactional search engines where you input a prompt and get a static response.
And instead, they start acting more like lifelong autonomous research colleagues that maintain an ever-evolving, perfectly curated internal state, a completely persistent agentic state. No more token exhaustion, just endless self-curated discovery. That is a brilliant thought to leave on. Thank you all for tuning in to this breakdown on AI Paperslop. For everyone building out there, take a hard look at your pipelines this week and ask yourself, are you just throwing compute at the wall and telling your agents to search longer, or are you actually designing for discovery, verification, asymmetry? We will catch you on the next deep dive.